Hello. So it's my pleasure to introduce the second speaker, Professor Janos Balog from the Wiener Research Center in Budapest. And, with Ivan, we met 44 years ago. No, 45. With Janos, we met 41 years ago when he was visiting from Hungary to back in Leningrad. So, so it will be a different style presentation about more about integrable quantum field theories, and but there is a continuity. In Wiener Hopf, Hopf is the same as Hopfling. So, Janos,
Okay.
please.
Thank you. So first of all, I would like to thank the organizers for inviting me to this nice place. And indeed, I will talk about work which we have done at Wiener Research Center in Budapest, together with Michael Abbott, Bajnok Zoltán, Hegedűs Árpád, and Vona István. The subject of my talk is perturbation theory, and the main question I will discuss is how can one make sense from the perturbation theory, which is in a typical quantum field theory is not convergent but only asymptotic. And I will discuss and solve this question in a toy model, a two-dimensional nonlinear sigma model. But more precisely, it's 1 plus 1 dimensional model, one space, one time dimension, as opposed to our real world where we have 3 space plus 1 time dimensions. So, first of all, I will recall the biggest successes and problems in perturbation theory, in quantum field theory. Then I will discuss Borel resummation, which gives partial answer to our main question, but as we will see, it's only partial answer. Next, I will introduce the toy model I'm going to solve in this talk. And from that point, my talk will become rather technical. So I will only sketch how the Wiener-Hopf technique solved the perturbation theory problem, at least in our particular toy model. And finally, I will present the full solution of our problem in a form of a so-called transseries, and present the solution in a form of a so-called median Borel resummation, which I will explain. Okay, so let's start with the successes of perturbation theory. Perhaps the biggest success of perturbation theory in quantum field theory is the calculation of the anomalous magnetic moment of electrons and muons. Now we know that the Dirac equation predicts that 1/2 spin fermion in certain units has magnetic moment G equals 2. But in quantum field theory, there are some corrections coming to that. And the difference between the Dirac prediction and the true value of G is called the anomalous magnetic moment. This can be computed in quantum field theory in this particular problem using quantum electrodynamics. And it has been computed up to 5 loop orders. And this expansion up to 5 loop orders is actually a lifelong enterprise. And indeed, Professor Kinoshita and his collaborators worked for decades to obtain this 5 term in this perturbative expansion. And the expansion parameter is extremely small in this problem because it is the fine structure constant, which is approximately 1/137. Now, the first term was computed by Schwinger in the 1940s, and the next term was computed, I think, at least 15 years later. There were several attempts, errors, corrections, but finally the result is given by this formula. I just, for curiosity, mentioned that this is built from rational numbers, pi squared, and the number zeta 3. Later we will see that In our toy model, it's similar. This pi square can also, pi square over 6 can also be called zeta 2. Now, the third 3-loop coefficient is also exactly known, but it's a quite complicated expression. The 4 and 5-loop have been computed only numerically. And if we put together these 5 terms, we find a number which agrees with the experimentally measured value up to 10 digits. So this is no, this is physics experiment. This number is physics experiment. Sorry?
How can they reach such a fantastic accuracy?
Well, that's an experimental question. So as you see, apart from the zeros, there are 10-digit agreement. And this is really a spectacular success of perturbation theory. For the muon, this is for the electron. For the muon, there is only 8-digit agreement. And some people even speculate that the difference between theory and experiment is a sign of new physics. Maybe a sign of new physics.
And how many digits do you have for the first correction? If you take into account only the first correction?
I think it's already 2 or 3. So, and also actually the 0, 0 is part of the result, because this is the difference. No, this is a challenge. Okay, so in other models like QCD, the situation is not so good. In QCD, one, instead of the fine structure constant, uses the running strong coupling constant, which runs with the energy like 1 over log, roughly 1 over log of the energy. Here, it's much more complicated theory, only 1, 2, 3, depending on the process, terms are known, and the energy range is such, that this running coupling is not extremely small, it's only 0.15. So here we cannot hope for many, many digits agreement. And one of the best studied example is related to the hadronic branching ratio of the tau lepton. It contains some well-known electroweak parts, plus the hadronic correction, QCD correction, which is called delta naught here. And the delta naught can be expressed exactly in terms of the so-called Adler function, which is the Fourier transform of the 2-point correlation function of the currents. And again, here we have 5 perturbative terms in terms of the running coupling. And these are the numbers. The first 2 are actually analytically computed. The rest, the 3 and 4, only numerically. And finally, the 5 is not really a computation. It is an estimate, an educated guess by very good expert of the field. And as you see, the problem is, first of all, the coupling for the tau decay is quite large, 0.3 only. And secondly, we only have 5 terms. And thirdly, the terms are growing. So this is, first of all, a practical problem, but also a problem in principle. And this is not an accident, because typically a perturbative series is divergent, and the divergence is such that the n-order coefficient for large n behaves like n factorial. And we also know why it behaves like n factorial, because the number of Feynman diagrams that are necessary for the computation grow like n factorial. But in addition, there are other sources of this n factorial behavior, so-called ultraviolet and infrared renormalons. These are individual diagrams which are anomalously large. For the infrared, for low energy, for the ultraviolet, for large energy. So our basic question is, how can we obtain the exact value of the physical quantity, knowing the perturbative series. And the partial answer is Borel resummation. So first step of this procedure is to study the Borel transform of the perturbative series, which simply means that because it's divergent like m factorial, we simply divide the coefficients of the series by this m factorial, and then it becomes convergent, at least in a certain convergence, within a certain convergence radius. And then we can, perform this Borel integral, which is claimed to give the physical answer. But as you see, this integral is from 0 to infinity. The original Borel function is only convergent in a finite range, so we have to analytically continue. For the purpose of this integral, analytically continue along the real line. And now the problem is that what happens if there are singularities along the real line of the analytic continuation. And actually, we know that typically there are singularities caused by, on the positive part of the real axis, by the infrared renormalons, but also by instanton solutions. And for the negative part, which is really not interesting for us because we are integrating from 0 to plus infinity, there are also singularities caused by ultraviolet renormalons. Now here, as usual in physics, if we encounter some infinity or problem, we regularize or modify the problem a little bit. And here the solution is that instead of integrating along the real line, we integrate slightly above the real line. This is called the lateral Borel summation S plus. But of course, we could also integrate it slightly below the real line. It's called S minus. And first of all, both S plus and S minus exactly reproduce the asymptotic series we started from, but they are not equal. So this is called the non-perturbative ambiguity. And for instance, in the simplest case, if we just have a pole singularity, just to see an example, then this non-perturbative ambiguity is proportional to exponent -1 over the coupling. So that's why it is called non-perturbative ambiguity. You can also see that actually in this simple example, this is purely imaginary. So a natural idea is that, okay, let's take the average of the two lateral Borel summations, which is, in this simple example, is just the real part of each, and propose that this is the physical result. But as we will see, this is, although this is a good approximation, it is not the full answer. So let's go to our toy model, because of course these questions are extremely difficult to study in the realistic theory like quantum electrodynamics or QCD. So let's study the same kind of question in a simpler setup, which is a two-dimensional quantum field theory, the O and nonlinear sigma model. Now this model looks like a free massless theory because the Lagrangian is just a kinetic term, but it is neither free nor massless. It's not free because there is an interaction generated by the fact that the field is a unit vector in n dimensions, so this constraint generates the interaction. And it also turns out to be massive, it has a mass gap. So why it is popular as a toy model? Because it's very similar, it has very similar properties to interesting realistic field theories like H theories. First of all, there is this coupling constant here. This is the bare coupling constant appearing in the Lagrangian, but it's a renormalizable model. So as usual, we can regularize, renormalize, introduce the running coupling, which I denote by alpha. And we observe that it is asymptotically free, just as gauge theories are. And another similarity is that there is dynamical mass generation. So just like in gauge theory, where there is a mass cap, although the Lagrangian doesn't show it naively. And in addition, this model also has instanton solutions, actually only for n equals 3. There are also instanton solutions for higher n, but those are unstable. But for n equals 3, we have stable instanton solutions. And
Certain restrictions pretty much the same as the same order. Why am I
well, for any n, you can actually, there's only instanton solution for n equals 3, but you can embed this solution to higher n, but they become unstable. Well, for n equals 3, I think the reason is why there are stable monopole solutions, because if you compactify space-time, then you have a two-dimensional sphere, and if n equals 3, then the target space is also a two-dimensional sphere. So there are topological mappings, and that's the reason why there are instanton solutions. But an important property of this model is that it is integrable as a quantum field theory, which is, of course, more than what we have in realistic gauge theories. And this integrability means that, in a sense, this model is exactly solvable. And for instance, the exact scattering matrix was established by the Zamolodchikov brothers a long time ago. So we decided to study the following particular quantity, because our philosophy is not that we are interested in the physics of this model. We just want to study the property of perturbation theory. So we happen to choose the following quantity. We consider a finite density state. That means that in a given interval, there are finite number of particles. And the question is, what is the energy of this finite density state? Now, these formulas, which I subsequent formulas, are for simplicity for n equals 4, because as we will see, in some sense, n equals 4 is the simplest case. So if we remove some simple prefactors, the rest of the problem for the energy density is perturbative. It can be expanded in the running coupling alpha. And for O4, the first few coefficients are computed using Feynman graphs. They are rational numbers. And the running coupling, in this case, runs with the density rho. Now, the exact solution for this energy density problem is given by the TB equation. This is the continuum limit of the Bethe ansatz equations for this finite density state. This is a linear integral equation, and the unknown of this equation is denoted by chi. This is the density in rapidity space, because theta is the particle rapidity. The right-hand side is just the one particle energy using the rapidity variable, and the kernel of the integral equation. Here comes the fact that this is an integrable model. It's just a logarithmic derivative of the S matrix, which is exactly known. Now, if we are able to solve this linear equation, maybe one ingredient I would like to emphasize is the capital B is denoted by capital B because this is the bosonic Fermi level. Because these particles are bosons, but due to the extremely strong interaction at low energy, they practically behave as fermions. So only one state per particle can be filled, like for fermions. And so our picture of this ground state at a finite density is that all available states, rapidity states, are filled by particles between 0 and this bosonic Fermi level capital B. And after the Fermi level, no states are filled. So this is our picture. And so therefore, this capital B is going to be our one of the most important variables. Now, if we are able to solve this linear integral equation, then the particle density rho can be expressed as an integral over the rapidity density, and the energy density can be obtained by the density in rapidity space weighted by the one particle energy. Now, the point is that this model can be solved perturbatively to arbitrary order very easily without doing any Feynman integrals, Feynman graph computations. And this is due to a trick of Mitrovolin, who actually, I think, registered participant in this conference, but I don't see him in this audience. So his trick was to first of all remove some simple factors so that the remaining expressions are just perturbative expansions in 1 over b. So in this problem, 1 over b plays the role of the coupling constant. And I'm unable to explain the details. I just tell you the result. The result is that the numerical coefficients in both the density expansion and the energy expansion, these numbers can be calculated without doing any Feynman graph computations, completely algebraically using some very ingenious recursion relations. So we can assume that these numbers are known, and indeed in the original paper, Mitrovolin computed up to 26th order, maybe motivated by the dimension of the string. But since then, up to 44 orders, there are analytic results, and numerical results. We computed numerically the coefficients up to 2,000 terms, which is unprecedented in perturbation theory and made possible by this trick. And finally, if we...
Are these series convergent or just formal series? Do they converge?
No, that's my problem. So these series are all asymptotic, all divergent. And so if we have the 1 over b expansion, we can transfer it to the running coupling expansion using this formula. Okay, so as I mentioned, we have 44 coefficients, and this is just because this is a mathematical physics conference, maybe just as a curiosity, we observed, and other people also observed, that all these coefficients are built from rationals and odd zeta numbers, but no even zeta numbers, which are powers of pi. This is not really important from what I'm going to talk about, but it's interesting, and it's an unproven thing. Maybe it's a challenge to prove and understand the reason why this is so. Now, so don't be happy, this is not the end of my talk yet, but I'm afraid I will run out of time, so I would like to summarize our results first and then go to the technical details. So what we were able to show is that this energy density, let's concentrate on the energy density, can be completely obtained in terms of a transseries. So what is a transseries? Is an expansion in terms of the non-perturbative expansion parameter, which I call nu. This is exponent of minus 2b. Remember, the coupling constant was 1 over 2b, so this is 1 over e to the minus 1 over coupling. This is the non-perturbative expansion parameter, and the expansion coefficients are actually all asymptotic series in the running coupling V. V is just related to B, which was our original variable by these implicit equations, where this constant gamma is 4 minus n over n minus 2, and this explains why I said that n equals 4 is the simplest, because for n equals 4, V is just 1 over 2b. For other n, it's more complicated, but the structure of the result is very similar. So we have this transseries, which is an expansion in terms of the non-perturbative parameter nu, and the coefficients are asymptotic series in the running coupling V. And our result is that using Wollin's result, we found an algorithm that determines all these coefficients here. So at least as a formal transseries, we have the final result. Actually, I put a tilde here, which means that this is the quantity in a form of a transseries. So by transseries, I mean this kind of expansion. Okay, and our main conjecture is that the physical result, which in our case actually could be obtained directly from solving the TV equation, but this is not my point, because we are not interested in the value of the physical result. We are interested in the structure of the physical result. And the statement, oops, I don't know why it is. What happens is that it is given by the lateral Borel summation of this transseries. By lateral Borel summation, I mean that we do the lateral summation term by term for the coefficient functions. And y plus, because there is an ambiguity also in this transseries solution, there is an ambiguity. It could be f plus or could be f minus. I will explain later how, where this ambiguity comes from. But the point is that this ambiguity in the transseries is compensated by the ambiguity of the Borel resummation. We have no proof for this main conjecture, but we are convinced that this is true. And we have numerically checked, and our best result for n equals 4 gives an agreement between the solution of the original integral equation and the lateral summation of the transseries up to 72 decimal digits. So beyond reasonable doubt, this is exact. And if you assume that this conjecture is true, you can derive interesting consequences of this assumption, namely that this can also be interpreted as the so-called median Borel resummation of just a perturbative piece, which is f naught. And this is actually only for n equals 3, which means that actually the perturbative series is enough to obtain the full physical answer. So I have time to 40,
Yes.
11:40. So so if we know just the original perturbative series f naught, this is actually contains all the information that is necessary to obtain the full answer. But you need to process this data. Okay, and now we see that if this is true, then it is not true that the physical answer is just the lateral summation of the perturbative series, but what is true that the perturbative series knows about all non-perturbative corrections, and in principle, knowing F naught, you can compute all non-perturbative corrections. Okay, for n equals 3, it's slightly more complicated because, as I mentioned, this is the only model among this, in this family of models that has stable instanton solutions. And it turns out that there are 3 asymptotic series that need to be computed. F naught is the original asymptotic series. F1 is the expansion around the one instanton solution. F2 is the perturbative expansion around the 2 instanton solution. And the physical result, which is still the lateral Borel summation of the transseries, can also be written as the median Borel summation, but in this case, not just the perturbative one, but perturbative plus 1 instanton plus 2 instanton. So this is the summary of the result, and now I go to the technical details. So it turns out to be useful to study, instead of the original TV equation, a slightly more general setup. So originally, the right-hand side of the equation was just cos theta, which is the one particle energy. Now we generalize it to cos n theta. N need not be an integer and can be any positive number. And otherwise, the left-hand side of the integral equation is similar. And we also study more general moments. So we solve this equation with right-hand side cos n theta and weight it with cos m theta, where m again can be any positive number. And although our main variable is b, and it's essential that everything depends on b, but as a notational simplification, I will not explicitly denote b dependence from now on. And what we are really interested in is this, in this previous notation, O11 and O10. The latter giving the particle density, the first one gives the energy density. Now, the reason why we can solve this generalized problem is that it is possible to prove that there are differential relations among these objects. And dot in this talk means derivative with respect to the variable capital B. It turns out that the derivative of the density is proportional to the product of 2 boundary values. So rho n is the boundary value of the solution. So the density in rapidity space corresponding to the maximum available density, which is capital B. The second differential equation is a second-order equation satisfied by these boundary values, where the right-hand side contains this function f, which important is that f does not depend on n. Of course, it does depend on b, but does not depend on n. And this structure shows that actually one object, if we are able to compute one object, we have all of them. Because, for instance, if we start from O11, then this first differential equation immediately gives us rho 1. Knowing rho 1 is sufficient to compute this f. If we know this f, which is n-dependent, we can integrate this second-order equation for any n. And if you have rho n for any n, we can integrate again to obtain the general ONM. So all objects are introduced are determined by just one of them. Now, it's the Wiener solution is a rather technical way of obtaining the solution of this type of integral equations. But if you let us go back quickly to the original problem. So as you see, this is a linear integral equation, and of course capital B is our important variable. But if it were from minus infinity to plus infinity, it would be just a convolution, which is trivial to solve in Fourier space. You just have to divide in Fourier space by the Fourier transform of 1 minus k. But of course, here it is much more complicated. But nevertheless, this 1 minus k in Fourier space plays an important role. And the Wiener technique starts with the factorization of this object into a function g plus, which is analytic in the upper half plane in omega, and g minus analytic in the lower one. And luckily, in this O1 model, we have this Fourier transform, which is a relatively simple function. We can do this factorization. And later, we will need the ratio of g minus and g plus along the positive imaginary axis. Now, g plus, as I said, by definition, is analytic in the upper half plane. G minus is not analytic in the upper plane, only in the lower plane. But it turns out that this particular function is actually also analytic on the upper half plane, except the positive imaginary axis, where it has poles and cuts, and a cut starting from 0 and also poles. So these objects will be important, and these are the non-perturbative data which are necessary for the solution. So there are poles for this ratio. These poles are equally spaced. The spacing is 2 psi naught, which depends on n, but for the most important models, O3 and O4, psi naught is actually equal to 1. And what is also important is the value of the residues, which is called the Stokes constant, SL. So these are important building blocks. And also important is the discontinuity. As I said, it has a cut along the positive imaginary axis. And so the jump here denoted by Bethe. And what is interesting is the jump itself is analytic. So it's a function with discontinuity, but the discontinuity is again an analytic function. It's Bethe, more precisely, meromorphic function, which doesn't have cuts, only poles. And important is that if we expand this apart from this exponential factor, the jump function, it is perturbative in this running coupling V. So perturbative means that it is an asymptotic series in integer powers of V, positive integer powers of V. Well, here it is important that this is a shortcut from minus B to B, but there are analogous equations from minus infinity to B, for instance. Very similar analysis holds, but the technical details are actually only for this shortcut. Okay, so it's important that this A is perturbative in a sense I explained, and we already introduced the non-perturbative parameter nu, which is e to the minus 2b. Now again, technically it is simpler to introduce to remove some simple factors from this density, and after removing the simple factors, the density is called W, and the boundary value is called lowercase w. And now the Wiener Hopf integral equation, which is nothing but the original integral equation in Fourier space, after deforming the contour. So in Fourier space, you integrate from minus infinity to plus infinity. If you deform the contour so that the first part comes down along a little bit left to the imaginary axis, the second part goes up a little bit right to the imaginary axis. That's the Wiener of integral equation. And here we actually modified already the equation by moving this contour to the left of the imaginary, for definiteness to the left a little bit of the imaginary axis, but rescaling this argument by an imaginary number, this equation now looks like a linear integral equation for the unknown capital Qn, where the integration goes slightly above the real axis. Plus, during the process of moving the contour a little bit to the left, we passed through the poles, which give some extra contributions. These are the contributions of the poles. So this is the Wiener of integral equation, which is equivalent to the original TB equation. Now this looks much more complicated than the original equation, but the big advantage is that now this can be expanded systematically as a transseries. And here the residues of the poles are multiplied by the value of the function at that point. So this Q is not an independent variable. This is just the unknown function at a certain point. So this is a closed, in principle, a closed equation, which allows us to determine Qn. And if we are able to compute this Qn from the Wiener of equation, then we can compute the boundary values, and we can also compute the densities. This is the simplified density after removing some trivial factors. So the next thing and next observation is that we can study the building blocks of this problem. So if we go back to this Wiener of equation and we remove all non-perturbative parts, then this is just a linear integral equation where the function appears plus an integral term plus the right-hand side. So this is the purely perturbative version of the equation. And we see that here actually this parameter alpha, which was previously denoted by n and was a positive number, it can be any number except 0. Because the important thing that I emphasize that this script A is perturbative, it can be expressed, expanded perturbatively in B. The right-hand side, of course, if alpha is different from 0, is perturbative in B. And assuming P is perturbative in B, we can systematically write down a set of equations and obtain the solution perturbatively term by term. This is what people did at first. But after Wollin's result, this is no longer necessary. We can just observe the structure and we can write down the solution in a second. But before we do this, we also observe that some densities will be important for us. And these densities, again, are purely perturbative because all ingredients are. And why these densities are important is because if we add 1 over alpha plus beta to this density, then this sum we call A, and this is just a purely perturbative part of the reduced physical densities. Okay, and now since we have differential equation for the exact solution, we can rewrite the differential equations for these simplified objects W, and also the same differential equations apply for the purely perturbative part, except that here we have to take the purely perturbative part of this n independent function script f. And as before, if we know just one of them, we know all of them. But from Wohlin's result, as I explained, we know A11, so we know all of them now. And this is just an illustration up to fourth order that this is how Wohlin's result for A11 looks like. And then the next step we determine using the differential equation A1, then the n-independent function script f, then the general, then A for the general, and finally A and M for general and M. But of course, this is only for loop order, but we have analytically up to 44 loop order and numerically for 2000 order. Okay, and now the next and final nice observation is that we have just solved the Wiener equation in the form of a transseries. And why is it is true? Because let's go back to the equation. So this is our Wiener equation. This is the first and the fourth term are the main part of the equation, and there is a right-hand side, and the main part and the right-hand side was solved perturbatively. But as you see, the non-perturbative pieces, as far as the x dependence goes, is exactly the same form as the right-hand side. And since this is a linear equation, we can immediately write down the solution because it's linear. And this is the solution. The first term is just a perturbative, and then the two non-perturbative terms give these two additional pieces. But using ingredients, all of which we know already. So we can now write down the complete transseries solutions. First, the equation for these constants, Q, tilde always means transseries. So as a transseries, this is a linear equation with two objects on the right-hand side. And these are the transseries form of the densities. So we can establish that the A, alpha, beta are perturbative information. Now we have all of them. Plus there are non-perturbative information. Actually, the fact that the pole structure of the poles equally spaced, this is also an important information. And the residues, the Stokes constant, are non-perturbative information. So for the energy density, there is a technical problem I didn't emphasize, that the two index N and M must not be equal for the general formula. So we are interested in the energy density, which corresponds to W11. We have to consider it as a limiting case, which is possible. But it turns out that this is the point where the n equals 3 and bigger than 3 cases are drastically different, because this constant n is non-vanishing for n equals 1, for n equals 3, whereas it vanishes for all higher n. Okay, and so my time is up. I need 2 more minutes. So for n equals 4, after doing the limit n and m both go to 1, the formula is like this, that first of all we have to solve a linear equation for the transseries, determine the constant q tilde, and after having determined q tilde, we can just write down the solution as a form of a one-term transseries. For n equals 3, is slightly more complicated because of the non-vanishing of this particular constant I mentioned. So we have two series on the right-hand side determining the q tilde constants, and for 2 times 2 series on the right-hand side determining the energy density. Actually, not for only 3, because it turns out that 2 of them are identical. And so now comes the main conjecture. And I just point out that we cannot prove the main conjecture, but we can obtain interesting consequences from it. But unfortunately, I don't have time to explain this. Instead, I just show our numerical results. And this is the TBA result. And the colored lines are the difference between the TBA results and the partial summation of the transseries. So if you just take the first or second term in the transseries and take the difference between the TBA, then on this logarithmic plot is a straight line showing that the difference behaves like the first non-perturbative correction, which we didn't take into account. And similarly, for if we take 3 terms, then the expected difference has a bigger slope, and the 4 terms and the 5 terms. And of course, this numerics is limited because the Borel summation has some numerical error, the TBA solution has some numerical error, but our best result is this point with 5 terms in the transseries, which is true for 72 decimal digits for n equals 4. So numerically, we convince ourselves that the main conjecture must be true. And finally, of course, the transseries is also an infinite series. So you might ask the question whether you gained anything, because what if it is also an asymptotic series, but apparently it is not. It seems to be convergent. So the question of convergence, if we ask whether it's convergent, we can give a very faint yes as our answer. Thank you very much. Numerically, but here in this part, it is given the leading coefficient of the various non-perturbative pieces. And as you see, the leading, because we can compute any number of leading coefficients, not numerically, analytically. And as you see, smaller and smaller. Of course, only consider the first 5. But if it happens to be 2, actually, if it is bounded, then it's okay, because then it's convergent. So that's why I said I give a very faint yes answer to the question. Thank you.
Thank you. Questions? Comments?
Do you know if this transseries gives you also an asymptotic solution to some nonlinear differential equation, like a Panlevé equation? So,
that's right.
So what is the Panlevé equation then?
Well, I think all this transseries and resurgent theory has been worked out using differential equations.
Yeah.
And the theory was worked out for this. So this is, I think, the first case where it has been applied to an integral equation.
But I mean, I think in, for example, the Ising model and so on, you get these integral equations also come out from the theory. So I would expect that there should be some Panlevé equation behind this.
I don't think so. It's too complicated.
You think
Okay.
Sorry, just a quick point. Do you think your approach can be applied to when you deform your, for example, O3 case and go to the sausage geometry, like Bethe of resumological?
I'm I'm sorry,
You
I
cannot
didn't
hear.
hear the
Okay.
question.
I mean, do you think now you have linear sort of integral equations? What if you go to NLIE, like happens in Bethe of Resummation, when your sphere flows into different geometry, like sausage model?
Well, the same technique can be applied to other models. So, in particular for the sausage model, I think you can have a similar structure in the Wiener Hopf. The difference is actually for the sausage, I happen to know that there is no cut. I mentioned that in our case, it was essential that this main building block in the Wiener Hopf equation had poles and a cut. And the sausage model, actually a sausage model in some limit becomes the nonlinear sigma model.
Exactly.
And only has poles, but not just one series of poles like this, but two series of poles. One of them is just equally spaces and remains, but both of them are equally
Asymptotic
spaced. But the
expansions.
spacing for one of them remains constant. For the other one, the spacing is smaller and smaller as you change the parameter that gives eventually in the limit the nonlinear sigma model. So somehow a condensation of poles gives you a cut. And maybe this is a better technique. So actually we were also thinking about this, that maybe it's actually, because if you only have poles, it's much simpler to analyze. And maybe it's a good way, even if you are only interested in a limiting case, good way to study the sausage first and then taking the...
Because
but of course, sausage in itself is also interesting.
you can take conformal limits, and there are many things that go consistently. So you see any renormalons in O3 as well? You can distinguish them? Sorry, I mean, do you see any in O3 case, which is a very special case, you can distinguish some renormalons as well?
Yeah, actually, we don't see neither the renormalons nor the instantons as such. So this is only our guess, that because the n=3 is so special, and the only thing we can think of is that it is caused by instantons, but we don't have any more proof that this is instantons.
Okay, more questions, more comments? If there are no questions, then thank you very much for this talk.